Good evening, everyone. My name is Shashwat, and today I'm here to explain the time complexity of various sorting methods. My registration number is 20 BCE 2818. So before explaining the time complexity of various sorting method, we must know what does time complexity mean. Time complexity refers to the amount of time taken by an algorithm to run as a function of the length of input. That is, the time complexity basically tells us that how fast are we able to achieve the given task or output which we want. Now, the best case time complexity is when we achieve our given task or achieve our desirable output in minimum number of steps. And the worst case is when we achieve our task in maximum possible steps. So that's what time complexity basically means. So we know the concept of insertion sort and how its time complexity functions. Today we'll learn about the time complexity concepts of bubble sort, selection sort, merge sort, and quick sort. Starting with bubble sort. Before understanding the time complexity concept of bubble sort, we must know what does bubble sort basically mean, or what happens in bubble sort, or what makes bubble sort different from other sorting methods. Bubble sort is basically a simple sorting method which works by repeatedly swapping the adjacent elements if their order is wrong. The order of comparison is always left to right. That is, we one by one we compare the elements, and then if the element is larger, we keep on shifting it from the left side to the right side. Now, to understand its time complexity, we must take an example. Let this the now we have taken the example 1, 2, 3, 4, 5, and 8 be an array which has 6 elements. So here already all now to calculate the best case, we assume that all the elements are in the correct sorting order. For the like in the example which you can see on the screen, 1, 2, 3, 4, 5, 8, they are in the correct order, that is the ascending order. So we don't need to sort them anymore. Thus, the algorithm will terminate in the first step only without any swapping being required. Thus, the number of comparisons is basically none, that is n minus 1. As the number of comparison is n minus 1, the best case will be on, like that, because, and the reason behind this is because we always take the maximum power of n as the best. Now, worst case complexity. Now, to calculate the worst case complexity, we assume that the array is in the descending order, because if it will be in the descending order, maximum number of steps will be required to to basically sort the array. So let's basically see the test case. Like assume that this 6, 5, 4, 3, 2, 1 is basically an array which is arranged in descending order. Now in the first iteration, 6 will be compared with 5, then with 4, then with 3, then with 2, and then with 1. That is, in the end, 6 moves to the rightmost position in 5 single steps. Then comes the turn of fifth 5, and then 5 move to the rightward position, that is the second position, in four single steps. Similarly, 3, then 2, and 4 move to their respective positions in 4, 3, and 2 positions. Moves basically. And in the end, 2 and 1 are swapped with each other. Thus, the total number of comparisons which are required during this iteration are 5 plus 4 plus 3 plus 2 plus 1, that is 15. Now, that's possible in this small example. But in general cases, the formula which we use is basically number of elements into n minus 1 into half, because half of the elements are compared and swapped on an average. Thus, the formula which we get is n into n minus 1 into 1 by 2. That's n square minus n by 2. Here, the maximum power of n is n square. That is, the worst case will be n square. That's what we learned in the bubble sort concept. Now we move towards the next topic, that is merge sort. Now, similarly, in merge sort is the best or the second most efficient sorting algorithm after the quick sort. It operates on divide and conquer principle. Now, we'll understand this concept later, but let's see what happens basically in merge sort. First, the elements to be sorted are divided into two halves. Continue this division until the sub-arrays of length 1 are created. That is, for example, you have this array, you keep on dividing it into two parts, and continue this process unless and until you obtain an array of length 1. Thus, now two sub-array, now once you obtain arrays of 1, 1, 1 length, then start merging them and sorting them simultaneously. So thus, in the end, the final result which you will obtain will be a sorted array. That what happens in merge sort concept. Now coming to the time complexity of merge sort. In merge sort, the time complexity is same in all the three cases. That is, the time complexity of best case, worst case, and the average case will be same. That is n log n. Now, and the reason behind it is that in merge sort, division and merging occurs in all the three cases. Thus, we have to merge all the arrays to obtain the sorted array. Thus, there is no best or worst case scenario developing in merge sort case concept. Now, again, we take an example. Now, consider n to be 2, 4, or 8. Generally, we are taking here as a like odd even numbers. We can also go for odd numbers. Only the number of steps will increase in that case. Iteration basically. So since we divide the array into two equal parts, thus even if we double n, we only increase the number of steps. So this concept means that even if we keep doubling the number of elements, only the steps of iteration are gonna increase. The rest of the process and the concept will all remain constant or same basically. Now in this question, to understand the concept, we have taken n to be 16. Now, so on each merge and sort stage, we have to merge and sort total number of n elements. Now again, here about 5 iteration steps are being required. Like here, the value of k will be 4 because 2 to the power 4. Then the number of iteration steps required are k plus 1, that is 5. So for example, this is the unsorted array 3, 8, 1, 7, 2, 5, 9, 4, 6, 11, 13, 15, 18, 21, 29, and 30. First we that's basically an array which this array is of length 1 only. Now we start merging like two arrays in a pair basically. So 3 and 8 are merged together, then 1, 7, then 2, 5. Similarly, other are also arrays. Once they are merged, at the same time sorting also occurs. Like for example, in case of 9 and 4, 4 and 9, the out in the after merging, 4 and 9 are obtained. That is, sorting also occurs. Now, once we obtain arrays of length 2, we again merge them to obtain arrays of length 4. Similarly, we keep on doing this until we obtain an array of length 16. But in the end, we observe that the array has been sorted. The reason behind is that merging and sorting are occurring at the same time. Thus, the end remains same in all the cases, only the divisions increase. Thus, division and conquer concept is being followed. So n can be written as n into 1 in first iteration, in second iteration n by 2 into 2, then n by 4 into 4, n by 8 into 8, and similarly in the end n by 16 into 16. Thus we obtain that this is the function which we get. Like in the end, n will be 1. So t n to power k is equal to t1. That is n to n by 2k is equal to 1. Thus the value of k which we get is log n to the base 2. Now we saw in the above example that always the number of iterations required are 1 greater than the value of k. So what we basically do is the total iteration will be k plus 1. That is, thus the end result will be n into k plus 1. So finally, the what we obtain is n log n plus n. Here again, the maximum power of n is n log n. So the time complexity in all the three cases of merge sort will be n log n. This is regardless of whether the input elements are pre-sorted or not. Merge sort is therefore no faster for any other process, right? Merge sort is not fast in any case or slow in any case. It remains same in all the three cases. Now after that, like now we have covered bubble sort and merge sort. Now we'll start quick sort. Quick sort is like the fastest sorting method, but it's also a bit complex. Like it's not that as simple as bubble sort is. Now quicksort also works on the principle of divide and conquer. First, we divide the elements into two sections, one with small elements and other with large elements. Now, this question might come into your mind that how will we divide the elements on the basis, like how we'll figure out that which element is small and which element is large. Now, the criteria is using the pivot element. Now, pivot element determines which elements are smaller and which elements are larger. Pivot element can be selected on using pivot strategy, what we say, and pivot strategy can be selecting the last element. That's a most probable case, or we can also select the middle element or any random element or median of three numbers or something like that. So this strategy continues till we obtain the sorted array. Like what we do that basically, for example, if we have an array, we select a sorting element, pivot element, and then we start swapping them unless and until we obtain the large and small numbers on two sides. Then we again find the pivot element of each small individual parts, and this process of division continues till we obtain our final sorted array. Now to again understand the concept of time complexity of quicksort, we like first of all we study about the best case complexity. Now the best case complexity, the quicksort achieves optimal performance if we always divide the arrays and subarrays into two partitions of equal size, because if we need n elements to be doubled, only one additional partitioning level will be required. That is, the best case scenario in case of quicksort is when we can divide the array into partitions of equal size. That is even basically what we are having in this case. This partitioning is done with the help of single loops within partitioning with linear complexity. Thus, in this, we have linear complexity. So the total effort remains same at all levels. Thus, just like merge sort, the best case complexity will be n times log n. That is the best case complexity is n times log n. How this functions, we'll explain that also. For example, this is a random array. I have not taken any example in this case. This random array has first of all has no partition. So this part that is 1 into n. Then we move towards this that we partition into two parts, then another two parts, and this process continues till we get single arrays. Now, what happens that again to calculate the what we say time complexity, we have to add all these. So while adding, we observe that again this kind of function is being obtained because in the end one will be there. So again the value of k will be log n and then k plus 1 division, because for example n is 4, then 5 iterations are required and so on. Thus the time best case complexity will be n log n. Now coming to the worst case complexity of our merge sort, quick sort. Now, if the pivot element is always the smallest to the largest element, that is because our input data is already sorted, or we always choose the last element as pivot element. That is, matlab, it basically means that the pivot element which we are gonna choose, like in general cases, we choose the last element as the pivot element. Like if the array is already sorted, like in ascending order or the descending order, then this is an obvious thing that if the last element would be the greatest or the smallest, thus it can never act as a proper pivot element, because on one side there will be n minus 1 element, like all the elements excluding the pivot element, and on one side there will be 0 element. So this using this, like if this kind of scenario exists, then we can't basically calculate properly the time complexity. So that's the worst case, that it requires a maximum number of steps to achieve the desired output. So this array would no longer be divided into two equally sized partitions, but one of length 0. Like as I said right now, one of length 0 and one of length n minus 1, excluding the pivot element. Therefore, we need n partitioning levels, each of size n, n minus 1, n minus 2, and so on. The partitioning effort decreases linearly from n to 0, obviously. Like the partitioning effort keeps on decreasing as we move down. And it is therefore 1 by 2. Like the partitioning effort is n into 1 by 2, that is n squared by 2. Because on an average that happens. So in practice, generally we see that this attempt might quickly fail because of stack overflow exception. Now, that's what we are seeing is that first of all, we had n elements in the array. Then we obtain one pivot element and then n minus 1. Then we again go for the partitioning, again two pivot elements. Thus, only the two parts which we are obtaining here, we don't have large part and small part. No, nothing like that. We only have a big part and a part which contains the pivot element. The pivot element can increase as the partition goes on. Like initially, we don't have any pivot element in the first step, then pivot element is 1, then 2, and that goes on. Thus, the worst case time complexity here will be n square. Now, how can we derive that? We can derive it using the normal method or even the recursive method. Now, this function basically we obtain tn plus is equal to tn minus 1, and then we can solve it and we get n square. Like the reason behind is that when we add all these elements, we get n plus n minus 1 plus n minus 2 and so on, and it continues till 2. Thus, we can write is that we know that the sum of n consecutive elements is n into n plus 1 by 2. And here this complete sequence does not have 1. So it will be n into n plus 1 by 2 minus 1. Thus the worst case time complexity here will be n square. Now we have covered all the like the three important ones, and the last selection is selection sort. Now selection sort is quite similar to insertion sort. Like what we saw in insertion sort and what we are going to see in selection sort are quite similar. The main difference basically in both of the sorting method is that in selection sort we obtain a like we keep on forming a new sorted array from the unsorted array, while in case of in insertion sort we insert the uh, basically the element in the correct position, but the process and concept is basically same. Now, so the selection sort sorts an array by repeatedly finding the minimum element from unsorted part and putting it at the beginning. The algorithm maintains two arrays, one which is sorted and other which is unsorted. So basically what happens, we find the minimum element. Now we have to find the minimum element, and then we obtain basically from an unsorted array, we in the end we obtain a sorted array. Now, again, let's take an example to understand this concept. Now, let n be equal to 6. That is, array has 6 elements, and the example is 6, 5, 2, 4, 1, 3. This is a normal unsorted array. So we observe that here we have basically two loops. So it's quite obvious that the complexity will be n squared. But we have to basically derive what the n time complexity is gonna come. So the time complexity of all of selection sort is all like again in selection sort also the time complexity is same in all the cases. The reason is also quite simple, because at every step you have to find the minimum element, and to find the minimum element you have to go and check till the last element of the array. So there's no like shortest step or longest step. We have to do the same thing in all the three cases. Thus we can't obtain average or minimum worst or best time complexity. Time complexity will be same because the process being followed is same in all the cases. Yeah, that is we have to go to and check the last element of the array also. So minimum like that is the minimum element is not known until the end of the array is reached. Like till we don't reach the end of the array, we can't figure out that which is the minimum element. So let's start with an unsorted array 652413. Now, like in the first iteration, we find the minimum element, which is quite clear that here the minimum element is 1. So 1 will be moved to the unsorted to the sorted array. Then after 5 comparison, this happens. Then we check which is smallest minimum element in this left unsorted array. Now we find that there's 2 after 4 comparisons. Then 2 moves. Similarly, after 3 comparisons, we get 3, then 4. Then in the end, we just after one comparison, we get the proper sorted array. Thus, we see that again here, initially the 5 comparisons required, then 4, then 3, then 2, then 1. Then the total number of comparisons required here also is n, basically 5, basically 15 here. This 15 can be obtained by n into n minus 1 into half. So now how half comes here, because half of the elements are unsorted on average. Like on an average, what we consider that half of the elements are generally unsorted. That's why we take half here. So thus n into n minus 1 by 2, that is and like here again the maximum power of n will be n square. So our time complexity will be n square. We can also add them in the normal method and then subtract n from it, and we get n square in this method also. Thus time complexity is O n square, basically n square in all the three cases. Thus, we have seen the time complexity concept of bubble sort, merge sort, quick sort, and then in the end, selection sort. And we have understood how the algorithm works, how the division takes place, how each sorting method is different from the other sorting method, and the pseudocode, etc. we have studied in the normal classes, but the time complexity concept is basically dependent upon the recursive method or the tree method, and we have derived it logically as well. So thank you, sir, for this DA.